Hello students, in the last class we learned about the composition of the turbine stator and the connection between the turbine guide and the casing. Today, let's learn about the cooling of the turbine blades. The turbine is the component with the largest heat load and power load in the engine. The adoption of effective cooling measures is a strong guarantee for the safe and reliable operation of the engine, and is also an effective measure to reduce the cost of high-temperature materials. In recent years, the annual increase in the temperature of the turbine inlet gas is inseparable from the effective cooling of the turbine, especially the rapid improvement of the air cooling technology inside the blades. According to statistics, the average annual increase in the gas temperature before the turbine is about 25 degrees C, of which about 15 degrees C is achieved by the progress of cooling technology. After the cooling blades are adopted, the increase in gas temperature has jumped, and the speed has greatly accelerated. This is not only due to the improvement of the performance of high-temperature materials, but more importantly, the improvement of cooling technology. In order to study effective cooling technology, we must first understand the temperature distribution and thermal stress of turbine parts, as well as their relationship with cooling measures. The figure shows the distribution of the gas temperature and the blade operating temperature along the blade height in an actual engine. It can be seen that the temperature at both ends of the blade is lower, and its maximum value is approximately in the middle of the blade. The stress is the largest at the root of the blade, and the temperature is expected to be lower. The blade is thinner at the tip, and the temperature is also expected to be lower to improve the fatigue strength of the tip. Based on the above distribution of turbine blade temperature, the following factors should be considered when designing the cooling system. First, for the cooling air used, the pressure flow, temperature, and cleanliness of the cooling air should be considered to improve the cooling effect. Second, the influence of the cooling airflow on the flow of the engine main channel should be as small as possible to avoid causing additional aerodynamic losses. Third, the temperature field after cooling should be uniform to reduce thermal stress. Fourth, reduce the leakage of cooling air. Fifth, strive for simple structure and reliable operation. Next, let's take a look at the design of the turbine guide vane cooling structure. The turbine guide vane is one of the most critical parts in the engine cooling system. Due to the different working conditions and positions of the guide vanes, the introduction of cooling air is also different accordingly. For the first stage turbine guide vane, since a double pivot connection structure is used between it and the casing, two airflows are generally introduced into the combustion chamber for cooling. The cooling air can be introduced from one or both ends of the blade to perform convective heat exchange on the inner surface of the blade. For the second stage guide vane, since it is connected to the casing by a cantilever structure with a fixed outer end, external airflow is generally introduced, and cooling air can only flow into the inner surface of the blade from the top edge plate for convective heat exchange. The cooled airflow will pass through the holes on the surface of the guide vane and flow into the mainstream. Next, let's look at the cooling of the turbine rotor blades. The cooling of the turbine rotor blades themselves can be divided into the following four types, according to the flow conditions and outflow methods of the cooling air inside the blades. The first is convection cooling, which can reduce the temperature by 100 to 200 degrees Celsius. The second is impingement cooling, which can reduce the temperature by 200 to 250 degrees Celsius. The third is film cooling, which can reduce the temperature by 200 to 400 degrees Celsius. The last is divergent cooling, which can reduce the temperature by more than 400 degrees Celsius. Convection cooling is a widely used cooling method. The cooling air flows through several special channels in the blade and takes away the heat through heat exchange with the wall thereby reducing the temperature of the blade and achieving the purpose of cooling. The cooling effect is generally 200 to 250 degrees Celsius. As shown in the figure, the first stage turbine rotor blades of the WP7A engine use convection cooling. The blade body has 9 small radial circular holes cast out of precision. There is a root extension, middle blade root, between the lower edge plate and the tenon. The cooling air flows into the blade body through the small holes on both sides of the root extension for convection cooling, which can reduce the blade root temperature by about 140 degrees C. Impingement cooling sprays one or more cooling air jets directly onto the surface being cooled, enhancing the local heat transfer capacity and cooling effect. Therefore, it is suitable for enhanced cooling of local high-temperature areas. From the principle of heat transfer, impingement cooling is essentially convection cooling. Therefore, impingement cooling is often accompanied by convection cooling, but the flow rate of impingement cooling is higher and the heat transfer coefficient is higher. The figure shows the cooling structure of the first stage turbine guide vanes of the WP7A engine. The cooling air enters from both ends of the circular tube and is ejected from the small holes at the front edge of the circular tube, strengthening the front edge of the cooling blade, and then flows along the inner surface of the blade, and finally flows into the main combustion gas from the small holes in the blade basin. Air film cooling is cooling air entering the inner cavity of the blade from the end of the blade, flowing out through a large number of small holes on the blade wall, forming an air film on the blade surface, isolating the blade surface from the hot gas and achieving the purpose of cooling the blade. The cooling effect is between 200 and 400 degrees C. Air film cooling has the dual functions of heat insulation and heat dissipation. The air flows along the surface of the blade and is heated due to heat conduction and turbulent mixing with the gas. After a certain distance, the air film loses its protective effect on the surface of the blade, and small holes must be opened to blow in new cooling air. The blades of the divergent cooling method are made of loose, porous materials. The cooling air seeps out from the inner cavity of the blade through the countless micropores on the blade wall, just like sweating. On the one hand, it takes away the heat from the wall surface, and on the other hand, it forms a layer of air film on the surface of the blade to separate the blade from the gas, achieving the purpose of cooling. The cooling effect is 500 to 800 degrees Celsius. Students, in this class, we have learned about the cooling of turbine guide vanes and turbine rotor blades. I hope you can remember the design of turbine guide vane cooling structure and airflow, as well as the 4 cooling methods of turbine rotor blades. Thank you.